spectrometry. The idea is that what we do is we weigh molecules with light. And this cartoon basically illustrated in the most simple and basic way. What we do is we shine light on our molecules. Our molecules each has optical properties that will scatter the light, and the amount of scattering, or here it's illustrated as the shadow, the amount of scattering is proportional to the mass of the molecule. And if we quantify this shadow or this scattering amplitude, we can quantify the mass of the protein. And this is the basic idea of mass photometry, weighing molecules with light. If I give you a really short introduction to mass photometry, it is based on interferometric scattering microscopy, and it's for single molecules. And here it's the basic setup of iSCAT or interferometric scattering microscopy. You have a laser, you shine light on your sample, most of the light goes through, some of the light is reflected, and some of the light is scattered from scattering object in the sample. You collect all the light that comes through from the sample, and you image it on the camera. Now, if we look at the sample cell, what we have is molecules that come to the interface of glass and water. Only when they are at the interface, they scattered light. You have also reflected light from the sample, and together you have the interference of the two. And what we see on the camera is basically the combination of the scattering light and the reflected light. And basically, it's a combination of reflectivity, which is here stated as R, the scattering light, and the interference between them. For biomolecules, the scattering is really, really small, and we can neglect it in this equation, and therefore we can define what is called iSCAT contrast, which is basically scattering, taking the scattering amplitude of the molecule divided by the reflectivity of the glass. And the scattering amplitude of the biomolecules is proportional to their volume, meaning that it's proportional to the mass divided by the density. And if we assume that the density of biomolecules don't change, basically what we have here is the scattering amplitude proportional to mass. So the iSCAT or interferometric scattering microscopy signal is proportional to the particle's mass. And this is quite strong, and it was already realized almost 10 years ago. However, it took a decade of optimization of the technique in order to really observe and quantify the mass of small molecules, of the small proteins. And here is basically the way, or some of the milestones along this decade of optimization. The most simplest one is basically taking more laser. You have more photons, so you can quantify it, quantify the signal better. There's also issues with the background and drift. And the most, I would say, important step happened 3 years ago, where basically it was understood how to enhance the contrast by reducing the reflectivity of the glass, or the signal of the reflectivity. And I wanted to show you what do we actually see in our experiments. So as I showed before, what we see in the camera is the combination of the scattering light and the reflected light. And if we look at the native movies, it looks like this. So you would say, okay, nothing happens here. It's actually quite, I would say, boring. But this is as a result of the fact that we have a really strong reflection from the glass-water interface. So we have to do some image analysis on that, and this is the way we do it. We calculate a background, and we divide it from the native images in order to see only the signal of the protein that come to the glass. And this movie is exactly the same movie, only with our image optimized image analysis. We call it ratiometric movie because it's we take out the background by division. And here you can see that actually the movie is really interesting. There are a lot of things happening here. And each one of those dots is a single protein. And we can see it really clearly. These proteins come to the surface, they bind, and then you see the scattering, their signal, and then they disappear. The reason that they disappear is because this background that we calculate is a moving background. So once they bind to the surface, we see their signal, and then they become part of the background, and that's why they disappear. And it's not that they diffuse or leave the surface; they stay bound to the glass. Okay, so what we have here is interferometric scattering microscopy for single molecules. As I said before, we have those particles, they come to the surface and only then they scatter light, and their scattering amplitude is proportional to their mass. And we can quantify and basically create this histogram of mass photometry contrast. And this is again something that I said before. The scattering scales linearly with the particle's volume and optical properties. And if we assume the refractive index of various proteins and their density vary by less than 1%, we can say that the contrast generated by each molecule should scale linearly with mass. And all you need is the calibration with known masses to correlate between the contrast and the mass. So what we do again is weighing single molecules with light. And I want to emphasize here that what we measure is really mass. It's not hydrodynamic radius or anything like that. What we do is measure the mass of the protein. And here, this plot is the expected mass of molecules measured by other techniques, most of which are based on mass spec. And this is the measured mass with mass photometry. And what you can see here is that what we measure is really mass, and it correlates really nicely with less than 2% mean deviation. And so what I showed you now until now is the basics, and you probably say, okay, but the technique, it probably really complicates, and how you do the measurement and how you do the experiments. Actually, it's super simple. And I want to show you here basically the instrument in action, how simple it is and how quick it is to do a mass photometry experiment. So here's a movie. Basically, the idea is that you add your sample to a slide cover slip. You close the lid, and then immediately you can see your protein lands. You start recording. The recording can take 1 minute, 2 minutes. It depends on how much statistics you want to acquire. So already within 2 minutes, you have your movie of protein, and you have all the data that you need. Now, all you need to do is the analysis. And this is done with our software, which is also super fast and can analyze movies within 1 or 2 minutes. So within, I would say, 5 minutes, you have an answer to what the content of, for example, content of your protein. And you can see here that you get your mass histogram really easily. So it's really a simple technique to measure the mass of your protein. So what are the benefits of mass photometry? It's an accurate measurement of true native behavior. The idea is that the measurement is in solution. So it's in native-like conditions. It can be done in various buffers, and it's also compatible with membrane proteins, and it's label-free. It's based on the properties of the molecule. You don't have to do any modification to the sample or any engineering. And the nice thing is it's applicable to many biological systems. It's including membrane protein, DNA, lipids. Because it's a single molecule counting, you can get information on all subpopulation in the sample and also web species. It can also provide you with wide mass range and high dynamic range. So you can get information about equilibrium and dynamic measurements, and also complex and multi-step processes is accessible. And it's one assay format that basically can give you multiple results. It can give you information about homogeneity, about structure integrity, about activity. It's really quick and simple and requires minimal sample amounts. And the analysis workflow are really nice and easy and intuitive, and it saves time on dedicated instruments. For example, if you want to take your sample to cryo-EM and you want to optimize and basically take the best sample, you can characterize it with mass photometry really easily, and then basically save time for example, in your EM measurement. So some ideas about the application of mass photometry. So the most, I would say, straightforward and easy is the quality control. Basically, the purity of the sample. Is there any degradation? Is there any aggregation in the sample? Are there any rare species? And the relative concentration of different species in the sample. The second is structure, basically oligomeric states and modifications. It can give you information about that. Of course, another thing is function. So it can give you information about interactions of different proteins with one another, and it can give you quantitative information about affinities and stoichiometry. And the last, I would say, application, which is now it's basically developed as we speak, is the assembly and disassembly of complexes and the binding kinetics. And what I'm going to do now basically is take you through a series of different applications and different systems showing this examples of all the applications and what you can do with that, and what can we benefit from mass photometry. Okay, so the first example is antibody aggregation, and it's really simple example of quality control of the sample. Here it's an antibody to G12, which has a tendency to oligomerize. So if you have your sample and it's in the fridge and you want to know what is the content of it, is it a good sample? Did it aggregate or not? What you can do is measure, and really easily you can quantify exactly how much of the monomer, which is at 150 kilodalton, and dimer and tetramer. And you need a really small amount. Here it was only 30 nanogram in the sample. So you get immediate information about the sample quality. And this is a really basic and simple example. Another example of quality control is for membrane protein. So here's in this example, it's BO3 oxidase, which is a membrane protein consists of 4 subunits. And what we did is measure it in element G, which is a detergent. And what we observe is a first peak at 190, which is the protein with a detergent belt around it. Since we measure mass, we measure the mass of all the particle, including its detergent belt. Now, it's debated if there is dimers of BO3 in vitro, and also the reason. What we observe in our samples is that we do have dimers, and as you can see, the amount of or their mass is smaller than twice the monomer. And the reason for that is because when you have a membrane protein with 2 which dimerize, the interface to the detergent decreases, and that's why you have a smaller detergent belt. And you can do some calculations, and this is what we did in this paper, basically showing that the amount of detergent belt that we measure correlates with what we expect. So again, what I want to emphasize here is that mass photometry can work with membrane proteins. It's not always simple as with other techniques. And it can work, however, it works, and it can work really nicely with different mimetic systems like lipid nanodisk, amphifold, SMARP, also detergent. So I told you that mass photometry can work with other biomolecules, and here is the first example of other biomolecule, DNA, which works really nicely and easily with mass photometry. And here it's also an opportunity to see an example of calibration curve of here specifically it's DNA length, and this is a DNA ladder. So it's a DNA length versus the contrast, and you can see how nicely and linear the linear dependence of the contrast to DNA length. Using this calibration, you can estimate the length of your DNA. Here specific, it's a plasmid, it's PAC 18, which is expected at 2,800, and we observed it 2,600. So mass photometry can also work with DNA really nicely. The last example in quality control, which I really want to emphasize because it really emphasizes our ability to measure mass, is AAV, which is adeno-associated virus, and it's a virus that is used to encapsulate some usually DNA in therapeutic, and usually there's because what we measure is mass, so we don't care about the shape of the particle. All we care about is its mass. So with other technique that do care about their shape, not necessarily able to distinguish between a loaded virus and an unloaded virus, loaded usually with DNA, we can detect it really easily, and we can, here's an example of how we can quantify the relative concentrations of the empty and loaded. And this is done in 5 minutes of measurements and analysis. which is a really useful, really useful tool for AAVs. Okay, so also, as I promised, mass photometry can give you information about the structure. And when I mean structure, I mean the structure when you combine different proteins. It is not sensitive to structural conformations of the same protein. So it's insensitive to structural changes below the diffraction limit. But if there is a change in mass, then we are able to observe it. And here, the example is with ribosome. And specifically what we want to show here is that we can study the stability of the ribosome in different buffers. So the full ribosome is the 70S, and it's here in this sample in its native buffer. You can see quite a large amount of the 70S. However, in the absence of magnesium, the ribosome disassembles to its subunits, subcomplexes, and you can basically optimize and try to study the structure at different buffer conditions. Again, one thing that I want to state here is that, of course, in order to calibrate properly the ribosome mass, you have to take into account that it's a combination of protein and RNA, and therefore you have to consider it when you do your calibration and quantify its mass. Okay, another example of structure, which is also related to studying it at different buffer conditions, is basically observing the disassembly of proteins with salt. And here it's an example from a proteasome, which is a complex consists of two sub-complexes. It's a huge complex. The 20S, it's 700 kilodalton, and 19S, which is 800 kilodalton. And it's an endogenous, specifically what I'm going to show you here, it's an endogenous purification. So basically each prep provides you with different ratios between the subcomplexes. And therefore, when you purify it with also cofactors. And you want to quantify exactly how much of the cofactors you have. And each preparation might give you different ratios or different amounts of these cofactors. So the basic, and I want to show you this equation or this reaction, which basically taking the 20S and combining it with 19S gives you the 26S, and another 19S can give you the 30S. And you can control the integrity of the 30S and also the 26S by salt. So this is exactly what we did. This is the control, the mass histogram of the control, and we can quantify exactly which species are present, including the species with the cofactor. So we have the 30S with the cofactor with the ECM29, or the 26S with ECM29. And as we add salt, we can observe the disassembly of the complexes, the 30S and then the 26S, together with the cofactors. And you can quantify exactly the relative amounts of each species and study the mechanism of disassembly, including, for example, how it behave with or without the cofactors. And these are something that we were able to observe. However, in this paper, we also correlated with negative staining EM, which they were not able to distinguish between the 26S or the 26S with the cofactor. So just because we are measuring mass, we were able to distinguish between the two. Again, another really great example of this quantification of the heterogeneity of the sample is by this APC, which is anaphase promoting complex. It's a huge complex of 19 subunits with three-step purification. And the idea is to study the structure of the protein with the cryo-EM. So you want to take the sample to cryo-EM. However, you want to maximize the amount of full complex in order to save time in your cryo-EM measurement. So you optimize the purification step, and you want to quantify which sample in your chromatography you want to take to your cryo-EM. And this is what we did here. Here's our the last two steps, which is ion exchange chromatography and two examples of the gels, and the size exclusion chromatography, and again examples of the gels. And from those plots, you cannot say exactly how much of the full complex you have. You can estimate it, but definitely not quantify it. And immediately when we measured our mass histograms with mass photometry for the different steps correlate to those illusions, just immediately by looking at that, you can say which sample is good and which sample you should take to your cryo-EM. Of course, what we wanted to do is really give it a number, so quantify it. So basically, we quantify exactly how much of the APC the full complex you have in the sample, and here's the plot. And we also correlated to these mass photometry measurements are in circles, and we quantified to what we would get in negative staining, and you see that it correlates really nicely. Only for us, all these measurements took maybe an hour, and for in negative staining, it took weeks. So it's really easy and simple tool to optimize and also get information about the heterogeneity of the sample. Now, the last example that I want to show you is that you can manipulate your protein and study the oligomeric state or the influence of the oligomeric state as a result of the modification. And here it's an example of FOXP2. It's oligomerize where the main species is around 100 kilodalton. And what if you just replace 3 leucines by alanines, here is in P2, you see that there is a drastic effect in protein oligomerization, and most of the proteins are actually in their monomeric state. Now, and you can quantify and study it in a really simple and easy way. Another modification that you can do is deleting part of it. Specifically, this is the ZF, which stabilize the protein and basically also dramatically change the oligomeric state of the protein. So just to basically summarize the last slides, the structure we can, with mass photometry, you can study the structure of your sample and its heterogeneity, as long as you have a mass shift in your different species. Now, we discussed sample quality, we discussed structure, and one really useful tool is studying interactions and function of proteins. And I wanted to start with a really useful example of antibody and antigen interactions. And this example published just earlier this year is of antigen, which is FcRn, which has a complex, I would say, interaction with the antigen. It can also, it can independently dimerize. So it's a competing reaction, and also it can bind to antibody, and it can bind it twice. And using mass photometry, what you can do is basically, first of all, even study the different species that can rise when you interact this antibody and antigen. So basically showing that there is oligomerization and also the ligand binding by two antigens, and also study exactly the KDs of the reaction, and also study it in different buffers. As I said, the mass photometry can work in different buffers. You can quantify it at different buffers, and this specific protein is known to be pH dependent. So based on the relative relative amounts of each one of the species, you can quantify its relative concentration, and therefore you can quantify the KD. And there is, of course, some sort of concentration limitation, which is between 100 picomolar to 300 nanomolar approximately. Really relevant, I would say, example is in the function or quantifying the protein-protein interactions is the SARS-CoV-2 example. Of course, it's known that the coronavirus is interacting with its host via its spike protein. And the spike protein interacts specifically with ACE2, or with human, it's ACE2 human. And you can basically isolate only the receptor binding domain of the spike, which here we termed RBD. And you can study the interaction and the strength of the interaction between the RBD and the ACE. And what we did here is measured with mass photometry, and this was together with Shira and Tamar from Weizmann Institute. So what we measured is the ACE molecule alone, which is approximately between 80 and 90 kilodalton. And we also combined it together with RBD at different concentrations of the two molecules. So either 2 nanomolar, 10 nanomolar, and increasing to 50 nanomolar. And you can observe really nicely the increase in the complex, which is around 120 kilodalton, the increase, and you can quantify exactly based on those plots. You can quantify where approximately the KD of the interaction lies, and it's approximately 20 nanomolar. So again, quantifying the affinity of the interaction. Now, all I told you until now are basically interactions of proteins with with other proteins. And for a lot of applications, there's need for quantification due to small molecules binding. And now our mass photometry cannot distinguish between a protein that binds to a small molecule, because the small molecule is too small to create a mass shift. What we can do is observe its effect if there is basically a structural change in the protein. And here is a really nice example of such a reaction. So basically what you have is 12-mer, 8-mer, and 16-mer. And without any small molecule, you don't have any 16-mer. However, when you introduce the small molecule, it creates this dimerization of the 8-mer. And here you can see it really nicely, and you can quantify it as a function of how much modulator or how much small molecule you add. So if what in this example, and this is for a pharmaceutical company, there are 3 modulators, basically 3 molecules which are candidate as a drug for this reaction. And they wanted to quantify exactly how much of this molecule do you need in order to create this effect of dimerizing the 8-mer. And you can change the concentration of the small molecule really easily, because it's just changing the buffer conditions and then measure. And since the measurements are really, really short, you can do a lot of measurements. And you see that, for example, for modulator 1 and 2, there is an effect at low molecular micromolar concentrations, and with modulator 3, there is no effect. So we can see a small molecule binding effects if they cause structural or mass shifts in your sample. One again nice example of complex protein interaction is the envelope glycoprotein of HIV virus. And so the envelope protein interacts with lactin, and the interaction is quite complicated, and the underlying mechanism it's not clear. So what we did basically is measured the envelope protein with different concentrations of ban-lac or lactin from bananas. And what you can observe is basically all those species you can observe in our mass photometry, even if there are at rare amounts. And you can quantify their relative concentrations, and then from that, from their concentration, basically come up with the mechanism of the mechanism of how they assemble. And this is exactly what was done here. The lactin concentration was increased gradually, and then each one of those species were monitored in terms of their relative concentrations, and eventually the mechanism with its affinity was specifically for each one of those reactions could be quantified. So one last example of function is for EMS or quicker EMSA, which is electromobility shift assay, basically quantifying histones. In general, histone concentration is difficult to estimate when you do this. measurement. The nucleosome assembly by histone titration is what is done here onto the DNA. And so if you measure the DNA alone, it can give you a signal. But then if you add histones, you can quantify exactly how much you have the DNA with either one histone, with two histones, with three, and you can do and you can see each one of those species and quantify exactly their relative amounts. And the nice thing, again, it's related to how quick and simple the experiment is. So last example that I want to give you is the dynamics, which here it's an example of the protein complex assembly over time. So this specifically is for complex with gold compound and protein, and basically it assembles through a period of around 20 minutes to its full complex, and you can monitor the shift in the main species. Here you can see here shift in mass of the main species through a period of around 20 minutes, and you can quantify exactly how or the dynamics of this assembly. Here it's shown nicely. So this can be done also for viruses assembly and for other particles. So I've given you a lot of examples of protein, of what mass photometry can do in bioanalytics as a bioanalytic tool. And just to return to this slide of benefits of mass photometry, it can give you accurate measurements of true native behavior. So it's in solution, and you don't have to add any modification to the sample, and it can be compatible with different buffers. It can give you information on subpopulations in the sample, so single molecule counting, and therefore you can see web species, and it can give you quite a wide range of behaviors, of masses. And as I emphasized, it's really quick and simple. It's one assay format, and it can give you a lot of information about the homogeneity, the structure integrity, the activity. And here's only some of the information. And thank you. This is my email. You are most welcome to contact me. I would be really happy to offer you demo sessions in Roichman to basically test some of the samples to show you how mass photometry can help in your research.
Thank you, Adar. There are many questions. You can find them in the question and answer section. I answered some of them, and you can see them all. Some there are 4 open, and also some questions that I answered, but you can go over them also with everyone.
So I'll start with the molecular weight range, because it's really actually an important point. So the official answer is minimum of 40 kilodalton, maximum of 5 megadalton. Of course, it depends on buffer conditions. Sometimes you can get to around 35. And sometimes you can get a tiny bit more than 5 megadalton, but this is kind of the range. And so the glass slide is one-time use. It's not a very special one, but it is in high quality. So it's relatively smooth, so that we will not be limited by the scattering of the glass roughness, because we do see the glass roughness scattering. So we need, I would say, special. They are not something that are really expensive. 100 slides costs around 20 euros or something, so it's not super expensive. And in terms of concentrations, I kind of wrote it a tiny bit, but it's the main limitation in terms of the concentration is from the low side. You need enough statistics to create this histogram. So we say around 100 picomolar, and towards the upper limit, the main limitation is that we want to quantify each protein by itself. So if we have overlaps, the quantification becomes less accurate, and then we are not able to quantify it properly. So we say around 100, 200 nanomolar. But this is, I would say, items in the sample. So if you have a protein that dimerize, then of course the monomer concentration will have to be shifted accordingly. So there is another question about, do you need a reference for mass calibration? So we do need to measure the contrast with known mass. Once we have the known, we have a contrast of something that we know exactly what is its mass, then we can create this curve of contrast versus mass, plot it with a linear linear dependence, and then we have this calibration, and it's usually good for at least one day. Sometimes it can be good for other days, but it's only one measurement, which takes 2 to 5 minutes. Okay, wait a minute. Sorry. So one question is related to the molecular weight difference. So as you observe, each one of our histogram has a width. The width is approximately 20. It depends it depends a bit on molecular weight, but it's approximately 20 kilodalton. So if you have two proteins that are 10 kilodalton apart, you might not be able to distinguish between the two. But 30 kilodalton in the range of 800 to 830, it's, I would say, challenging, but needs to be checked. So there's a question about, can we get the presentation? I think there's a recording, and you will get the recording. Is that right, Nitzan?
Yes.
Okay. What is the price range? This is something for Almog to answer.
Yes, if you ask for a price, we'll send a price quote. If anyone is also interested in, please write your email, and we will contact you later today.
Okay, so what is the expected error in the measurement as a function of molecular weight? So usually we say that it's around, so there's of course the width, which is approximately 20 kilodalton, but it's increasing as the mass increases. And we say in terms of precision, it's approximately 2% precision. And concentration, I think I already answered.
There are more open questions.
Yeah, that's what I'm going.
Yeah.
So how much plasmid DNA? If you mean what is the concentration of the plasmid, then it's exactly the amount of proteins. So around, I would say, low nanomolar range. There's a question about what is the Z distance for detectable scattering signal? Yeah, so what we say is that we detect only particles that really bound to the surface. There is I would say depth of field of a few nanometer, but since the particle move quite fast and we average everything, then basically only particles that really come and bind to the surface are detected in our software. So there's another question about the calibration of the molecular weight. Again, it's done by known molecules. Usually what we prefer is molecules that we know has different oligomeric states. For example, urease is a protein that is known to have species at 90 to 70 and 540. So within one measurement, you have 3 data points for the calibration. So usually that's why we prefer that. And you can, as long as you know the mass, the mass of your protein, you can use whatever you want. So possibility about demoing the instrument here in the campus. This is again something for Almog. There's a question about what is the resolution of small molecules addition. Can you say modifications by 8.5 kilodalton? So this is a kind of similar to what I've answered before. Our width is 20 kilodalton. So I would say the best, I would say, to distinguish between 2 separate peaks would be 20 kilodalton and more. However, if you have a peak that you know broadens as a result of adding something, then it might indicate that you have another species there. So it really needs to be checked on specific cases, and then you can observe really if you see this mass shift or not. So it's really based on that. So then there's another question about shape, and this is something which we are working a lot to basically I would say completely answer it fully. For now, what we saw and also showed is that if the protein is below the diffraction limit, so I would say below 100 nanomolar, any structural changes of the molecules, conformations and all of those, which will not cause mass shift, we are not sensitive to them. So everything will fall under the same peak, and our noise or our noise sources will give you a broadening of the peak, which are larger than the broadening due to structural changes. And that's why it's insensitive to structural changes. And we showed it for several proteins, one of which is cohesin, which is known to show really completely different configurations, which we were not sensitive to. And if it's important, I would be happy to send you the reference for that. So there is another question about what is the minimum affinity you were able to measure. And this is related to the concentration range. So basically what you want to do is measure the affinities at your concentration range. So if you have let's say towards the upper one, but micromolar range will be a problem, because if you measure at nanomolar range, you will not be sensitive, and you will see basically only the dissociation of the two complexes, and you will not see the complex, almost not. So I would say, as long as the affinity is within our concentration range, it's something that we can measure, which is approximately between 100 picomolar to 100 nanomolar. So there is another question about if I do first the calibration on specific slide and then run the real experiment. So the calibration is done just as another experiment. Usually what we do is we have the glass cover slide, we put in on top of it gaskets made of silicon with wells, in total 4 wells, meaning that on each cover slip you can do 4 experiments. And the calibration is just one experiment out of the 4. So I do the calibration, I calibrate it in our software, and then move to the other well and do another experiment, which is whatever I want. So it's just another experiment in my I would say day. Of course, I do it first because I want to afterwards measure with mass and not with contrast. But it's just one measurement. If you have a protein which oligomerize and do and has several peaks, if you need to do for 2 proteins, then it's 2 measurements, etc., etc. From my experience, if you have the proper calibration candidate, what I usually use, for example, is ureas, is you need 1 measurement and that's it. You're done for at least the next few hours.
But Adar,
yeah,
you can also, if you have repeated the measuring a repeated experiment, you can use a recorded calibration also.
Yeah. So
right?
the calibration, you do the measurement in terms of it's one more experiment. You analyze it, and then you get your mass. It's not mass, it's contrast histogram of your calibrant, and then you for each contrast histogram, you basically have your peaks, and then you calibrate the position of each peak with its known mass, and then it's saved in the software, and you can use it in your analysis throughout the day. And it's good throughout at least 3 or 4 hours if you work consistently. If you want to measure it, if you work on a different day, then usually I would say do another calibration for this specific day. But for your measurement throughout 4 hours, you need only one calibration, which is saved in your analysis. It seems like it's complicated, but actually it's super simple. And that's why I really think that coming for a demo really illustrate how simple it is and how intuitive it is. Yeah, so one more question is about the scattering amplitude, which is ignored in one slide, but then you tweet it. So this is actually thank you for raising it, just to make sure it's clear. So what we see on the camera is a combination of the reflected light and the scattering light and the interference between them. Now, the reflected light is huge. It's really strong and it's quite, I would say, large. And you have the interference, which includes the reflected light and the scattering light, which is S. It's the combination between the two. And then you have the scattering light alone, which is also squared. So within this equation with all its term, the scattering light alone is really negligible. So basically you can really ignore it. And all you are left with is the reflectivity and the interference, which is a multiplication of S and R. And that's why you keep basically the S, and that's why you have it. Now, the reason that we defined the ISCAT contrast as the scattering divided by the reflectivity is exactly because what we do is divide by the background, and the background we treat it only the reflectivity. So basically you are left with S divided by R. Yeah. So there's another question about the upper concentration limit. What we usually say is around 100, 200 nanomolar, but it's really sample dependent because you want to make sure that each molecule is basically quantified really nicely. So you don't have overlap of proteins. As long as you don't have overlap of protein, you can even go higher. So but in general, I would say the answer is around 100, 200 nanomolar. Wait a minute. There's another question about the calibration. Does every measurement require calibration? Again, you can do one calibration in the beginning of the day, assuming that you use only proteins and you can measure proteins. But if you now change to DNA, you have to do another calibration for DNA. But only one calibration throughout, and of course buffer conditions. So if you change your buffer conditions, then you need to do another calibration to account for the changes in the optical properties of the buffer. But as long as you keep the buffer the same throughout your all measurements, you need only one calibration. And this calibration is used for all your sample. Yeah, so mass calibration procedure for detergent solubilized membrane protein. So for membrane proteins, so the question is basically, if you have a membrane protein, which is it's used with detergent, how do you do the calibration? And this is really specific for sample specific. Usually what we do, because we quantify only also the detergent, then what we do is quantify only the protein content and assume that the detergent might shift in terms of the mass. So we won't necessarily quantify it in accuracy, because we don't have a calibrant for the detergent. So we usually, or at least when I'm doing the measurements for membrane proteins, I do protein calibration, and then I measure it with and get an information, including the detergent belt. And I assume that the detergent belt might be a bit shifted towards one way or another, so it's not quantified to an exact mass. But anyway, so this is something that I would be really happy to discuss in person, because it's really sample specific, and I would be really happy to give specific advice. So the question is, if the binding is long, is the peak narrows? So usually the narrowing of the peak is a combination of the noise in the sample and the heterogeneity of the molecules. And let's say that you have two proteins which are really distinct in terms of their mass, I would say 100 kilodalton difference, then I would assume that it will not affect significantly the peak width. This is my estimation. Another question is related to concentration in terms of, can I do the experiments at 10 or 20 micromolar? The answer is usually no. We work at nanomolar concentration. What if it's really important to work at high concentrations? What we usually recommend is doing either immediate dilution. So basically take this 10 and 20 micromolar, dilute it exactly to the well, and then measure it within 1 minute. So you try to capture as much of the species that are present at the high micromolar range. Or another option is to cross-link your sample and then dilute it. So then you still see the amount of or similar species to the high concentration sample. This is usually what we recommend. And the, I think, last question is, yeah, so it's again related to the micromolar range. So we will not be able to work at micromolar range, and there are some ways to bypass it. And again, it's sample specific, and it has to be tested. Since it's really easy to test it, it's something that can be just tried and see how it goes. And I hope I answered all the questions.
I think it seems like it. So I want to thank you, Adar, for the interesting seminar, and I would also like to thank Sasson, the head of the core unit that organized this seminar with us. I will send we will send everyone the presentation. Gal also wrote our emails in the chat, so you can email us if you want to have more information or just the presentation or price quote. We are here. Thank you, everyone. Have a great day.
Thank you. Please email me if you have any more questions you want to discuss, want to chat in person. I will be happy to answer anything.
Right. Thank you, Adar. Bye bye, everyone.